This work is a cross-functional collaboration with many talented peers at Pinterest, because deploying inclusive AI in the product requires a multidisciplinary approach, not just technical skills. So I would like to start by sharing some feedback a pinner sent us a few years ago. She told us that to see people of color in our app, she needed to physically type the word black, and that when she looked at our app, it told her that people who looked like her were not the norm. Pinterest's vision is to bring everyone the inspiration to create a life they love, and to truly be a place where everyone can find the most inspiring and relevant content for them. Pinterest is committed to content diversity and to building an inclusive experience on the platform. So AI powers many advanced search and recommendation systems at Pinterest. And these systems tend to be very complex. They have many components because they need to operate at the very large scale of over 400 million global monthly active users who have saved more than 300 billion pins to over 7 billion boards in over 35 languages. And we strive to be a place filled with positivity for pinners. Now, a top request we hear from pinners is that they want to feel represented in the product. This is why we launched the Skintone ranges and hair pattern search. These inclusive features give control to users on their experience in search and AI try on similar looks, by enabling them to narrow down search results for beauty according to a skin tone range or a hair pattern of their choice. Now, how did we build the skin tone ranges? I would like to walk you through that journey. In the early days, to understand the skin tone range in a beauty image, we considered a third-party closed-box computer vision library. It had a deep learning module for face detection, followed by color extraction. We got the LAB coordinates, threshold on the L score, and estimated the skin tone range. We launched this in production, and we heard positive feedback from our pinners who saw their experience improved. In particular, it became easier for them to find more relevant content in the darker skin tone ranges. However, over time, we started noticing issues with the closed box version based on visual inspection. But to be able to make progress, we needed to quantify the extent of the issues. So we collected a diverse data set and conducted an evaluation of the closed box on this data. The confusion matrix on the left revealed a major coverage issue in the darker ranges. And we also noticed performance disparities in the granular precision, recall, and F1 score for the closed box prediction. So in an image, this is how it looked like. The top row shows ground truth dataset, diverse dataset labeled by the specialist. And the middle row shows how the closed box understands the skin tone ranges for these images. As you can notice, it has a major coverage issue in the darker skin tone ranges. And it also failed to understand accurately the skin tone range for many images. Now, to understand why this was happening, we conducted an error analysis of the components of the system. The score distributions per skin tone range showed at the top right corner were not really separable. They overlapped. And the thresholds were out of tune with the diverse data. And these issues can be amplified by challenging lighting conditions and by shadows. Then when we looked at the output of the face detection module, we realized that the coverage issue was coming from there, because the face detection module was failing to detect faces at much higher rates for darker skin tone images than for lighter skin tone images. And this type of bias in face detection technology has been studied and documented by Joy Buolamwini and Timnit Gebru a few years ago. So we reached the conclusion that there was no amount of post-processing for fairness that we could do on the output of the closed box that could fix the built-in biases in its components on which we didn't have control. And so we needed to build our own system end-to-end in-house, and this is what we did. So in the first version of the visual skin tone developed in-house, we built a system with several machine learning components. After exposure correction, it detected the location of the face, extracted facial landmarks such as eyes, nose, and mouth, segmented them out to produce a skin mask. And in the cases where the face detection did not detect a face, the hue saturation value module detected patches of skin pixels in the image. The skin mask was then fed into color extraction, We got the LAB coordinates, computed the individual topology angle, and we fed that into a fairness-aware tuning phase that took as input diverse data to estimate the Skintone range. Now, when we evaluated this on the diverse data set, it was performing much better. The confusion matrix was closer to a diagonal and more symmetric. The score distribution per Skintone ranges were more separables, and the per Skintone range precision, recall, and F1 scores were not only higher for every Skintone range, but also the disparities in performance had reduced, meaning that we had reduced bias. Now, you've seen the top portions of this image, and the bottom row shows how the visual Skintone performs on this diverse data. We didn't have anymore the coverage issue for the darker Skintone range images, and while it was not perfect, we had made a lot of progress. But that was not the end. Even our in-house visual Skintone could make errors, and we learned from those errors and made the model learn from these errors too. So I'd like to share a few examples that tripped the model with you. Extreme lighting conditions are challenging. Occlusions, such as beards and sunglasses, can lead to errors. And then the pandemic happened. And as the world changed, so did images on Pinterest. The pandemic caused a surge of face mask images to which the model had to adapt. In some images, you have multiple faces or a combination of faces. In some images, the face is not visible, or there is no face at all because we also have other body parts. And so these use cases prompted us to search for a more robust approach. So we invested in collecting our largest and most diverse data set for Skintone ranges. It consisted of errors from the previous models, partial faces and body parts to handle new use cases such as lips and nails, other verticals beyond beauty such as fashion and internationalization. And for this model to handle more complex images, we decided to move away from face detection entirely, and we explored different machine learning architectures. This ResNet model, when evaluated on this more diverse and complex data set, outperformed the face detection approach. Next, we integrated the Skintone predictions into Pinterest multitask visual embedding model and added a Skintone classification task. And that model outperformed face detection and the ResNet model. Now, we built on our learnings from building the Skintone ranges with bias mitigation to develop hair pattern search. Hair pattern search is also powered by a computer vision model trained on diverse data to understand the visible hair pattern in an image. To define the hair patterns categories, we worked with hair experts who work with Black, Indigenous, and people of color, such as Naima Lafont, who is a Pinterest creator and the global artistic director for Amica, a hair brand. Their guidance, the help of our beauty and fashion specialists, and our user research team guided the development and our technical choices throughout the efforts to build hair pattern search. To mitigate bias and ensure that this system performed well across various segments of Pinterest data, we collected a large, diverse data set for hair-related images across skin tones and genders and hair patterns and hair-related interests. We integrated hair pattern prediction into Pinterest's latest multitask visual embedding model that leverages the vision transformers and also our investments into our computer vision infrastructure to scale to billions of images. Now, the Skintone ranges and hair pattern search provide a more inclusive experience by giving control to the users on their experience. But we would like also for everyone to feel welcome and represented on Pinterest from the start of their journey. This is why we launched Skintone Diversification in various surfaces, so that no one has to work harder to find content that's relevant for them. We've diversified according to skin tone, search results for beauty and search queries, fashion products in our shopping discovery surfaces, and we welcome new users with a diverse initial home feed when they first join Pinterest. Diversification approaches aim at re-ranking the contents so that the pins that are surfaced to the users are diverse by default. One common and simple approach is to boost the utility scores of pins that match a certain diversity attribute. While boosters are simple to implement, they tend to become tech debt, as they are tuned at the time where they are introduced, then forgotten. More boosters get added and are not jointly optimized. So an alternative is diversity-aware re-ranking. And our approaches to diversification evolved over the past couple of years from simple greedy re-rankers to multi-objective optimization. So we started with simple greedy re-rankers that take as input a list of pins ranked by their utility scores and the skin tones of those pins and score thresholds. And those re-rankers iterate on that set of pins to produce a diversified ranking. We deployed that in production, and it proved to be an efficient approach to increase diversity while having a neutral to positive impact on utility metrics. However, greedy re-rankers do not balance the diversity-utility trade-off. They do not generalize easily to multiple diversity dimensions, and handling multiple thresholds for various scores is just not scalable. So we evolved our diversification approach to a multi-objective optimization framework that can balance various utility functions and diversity using DPP, determinantal point processes. DPP is a machine-learnable probabilistic model that's used in physics to model repulsion and more recently in the recommender systems. DPP can be parameterized by a kernel matrix whose diagonal entries represent the utility of a pin, and the off-diagonal entries represent the similarity between pairs of pins according to some diversity feature. And per that model, the probability of an ordering of pins is proportional to the determinant of the kernel restricted to that subset. It increases with the utility of the selected pins and decreases with their similarity. So when we try to maximize the determinant, we obtain an ordering of pins that's high utility and high diversity. And thanks to its submodular property, the DPP solution can be efficiently approximated using a greedy algorithm. So DPP, when we launched it in an experiment, it performed on par in terms of utility and diversity when compared to greedy re-rankers. But it was able to balance diversity and utility in a flexible way that allowed us to expand the coverage of diversification to more queries in beauty and fashion, and to more diversity dimensions. So this is an example for the query short hair, where the score thresholds in the greedy re-rankers limited its ability to diversify, whereas DPP's flexibility allowed it to generate a ranking that was both high utility and high diversity. So to conclude, I would like to share with you some recent feedback that pinners sent us. Hearing from pinners that we are making a positive difference in their lives has been the most encouraging reward for our teams. And I would like to leave you with a message of hope that change in technology is feasible if one is intentional about it. Thank you very much.